So this is part 284C3J. So it's line 22f1fa19c3j Snell's law, calcite crystals, velocity, refractive index, 5G Wow Seti. There's the alien radio signal. So Snell's law from calcite crystal data talks about velocity and interface and normal, P and Q's. Okay. So in optics, the refractive index, or index of refraction, N of a substance, optical medium, is a number that describes how light or any other radiation propagates through that medium. Its most elementary occurrence, and historically the first one, is the Snell's law of refraction. N1 sin B1 equals N2 sin V2, where 0 and 02 are the angles of incidence of a ray crossing the interface between two media with refractive indices of N1 and N2. Brewster's angle, the critical angle for total internal reflection, and the reflectivity of a surface also depend on the refractive index as described by the Fresnel equations. More fundamentally, N is defined as the factor by which the wavelength and the velocity of the radiation are reduced with respect to their vacuum values. The speed of light in a medium is V equals C to N, or divided by N, where C is the speed in a vacuum. Similarly, for a given vacuum wavelength, A and O, the wavelength in the medium is A equals AO divided by N. This implies that vacuum has a refractive index of 1. Historically, other references media, example air at a standardized pressure and temperature, have been common. Refractive index of materials varies with the wavelength. This is called dispersion. It causes the splitting of white light in prisms and rainbows and chromatic aberration in lenses. In opaque media, the refractive index is a complex number. While the real part describes refraction, the imaginary part accounts for absorption. The concept of refractive index is widely used within the full electromagnetic spectrum. From X-rays to radio waves, it can also be used with wave phenomena other than light, like sound. In this case, the speed of sound is used instead of that of light, and a reference medium other than vacuum must be chosen. So for material, gases are at 0 degrees Celsius in one atom, and then it's got air, helium, hydrogen. Well, I'll just let you read it there. See? It's got all these different equations for stuff. Okay. So it says selected refractive indices at A equals 589 nm. For references, see the extended list of refractive indices. So July 30, 2012 was when I was working on this, and today is August 27, 2012. So my thoughts. So this is the formula I got from the keywords, okay? So your keywords are helium plus hydrogen plus carbon dioxide plus liquids plus water plus ethanol plus benzene plus solids plus ice plus fused silica plus glass plus diamond, all found in previous WOW data videos. All those keywords have come up before. Refractive index below 1. A widespread misconception is that since, according to the theory of relativity, nothing can travel faster than the speed of light in vacuum, the refractive index cannot be lower than 1. This is erroneous since the refractive index measures the phase velocity of light, which does not carry energy or information, the two things limited in propagation speed. The phase velocity is the speed at which the crests of the wave move and can be faster than the speed of light in vacuum and thereby give a refractive index below 1. So I guess the neutrinos did that, right? This can occur close to resonance frequencies for absorbing media and plasmas and for X-rays. Okay, so you can do this with a plasma, and one of the things that we had in the formulas was a plasma. Okay, so in the X-ray regime, the refractive indices are lower than, but very close to 1. Exception is close to some resonant frequencies. As an example, water has an refractive index of 1 minus 2.6 times 10 to the 7 at a photon energy of 30 keV, 0.04 nm wavelength. So this has a photon energy that it's talking. Water has a photon energy, and you had 2 photon cells show up in the Higgs boson particle. So negative refractive index, negative index metamaterials. Recent research has also demonstrated the existence of the negative refractive index, which can occur if permittivity and permeability have simultaneous negative values. This can be achieved with periodically constructed metamaterials. The resulting negative refraction, i.e. a reversal of Snell's law, offers the possibility of the superlens and other exotic phenomena. At the microscale, an electromagnetic wave phase speed is slowed in a material because the electric field creates a disturbance in the charges of each atom, primarily the electrons, proportional to the electric susceptibility of the medium. Similarly, the magnetic field creates... There you go. Sorry, I'm going ahead of you. The magnetic field creates a disturbance proportional to the magnetic susceptibility. As electromagnetic fields oscillate in the wave, the charges in the material will be shaken back and forth at the same frequency, like a milkshake. The charges thus radiate their own electromagnetic wave that is at the same frequency, but usually with a phase delay, as the charges may move out of phase with the force driving them. See sinusoidal-driven harmonic oscillator. Harmonic oscillator is a keyword, so is sinusdally that came up before in the WOW videos. The light wave traveling in the medium is the macroscopic superposition sum of all contributions in the material. The original wave plus the waves radiated by all the moving charges. This wave is typically a wave with the same frequency but shorter wavelength than the original, leading to a slowing of the wave's phase speed. Most of the radiation from oscillating material charges will modify the incoming wave, changing its velocity. However, some net energy will be radiated in other directions or even at other frequencies, scattering. So depending on the relative phase of the original driving wave and the waves radiated by the charge motion, there are several possibilities. If the electrons emit a light wave which is 90 degrees out of phase with the light wave shaking them, it will cause the total light wave to travel more slowly. This is the normal refraction of transparent materials like glass or water and corresponds to a refractive index which is real and greater than 1. If the electrons emit a light wave which is 270 degrees out of phase with the light wave shaking them, it will cause the total light wave to travel more quickly. There you go. That's how you get your neutrinos to travel quickly. This is called anomalous refraction. It's observed close to absorption lines with X-rays in some microwave systems. So if you want the electrons to emit a light wave, so you have to create some sort of light wave with electrons and neutrinos in order to get them to, and then shake them around, collide them, and that'll get your wave to travel more quickly. It corresponds to a refractive index less than 1, even though the phase velocity of light is greater than the speed of light in vacuum C. The signal velocity is not, as discussed above. In the response, if the response is sufficiently strong and out of phase, the result is negative refractive index, discussed below. If the electrons emit a light wave which is 180 degrees out of phase with the light wave shaking them, it will destructively interfere with the original light to reduce the total light intensity. This is light absorption in opaque materials and corresponds to imaginary refractive index. If the electrons emit a light wave which is in phase with the light wave shaking them, it will amplify the light wave. This is rare but occurs in lasers due to simulated emission. It corresponds to imaginary index of refraction with the opposite signs as absorption. For most materials at visible light frequencies, the phase is somewhere between 90 and 180 degrees, corresponding to a combination of both refraction and absorption. Because of dispersion, it is usually important to specify the vacuum wavelength at which a refractive index is measured. Typically, this is done at various well-defined spectral emission lines. For example, ND is the refractive index at the Fraunhofer D line. The center of the yellow sodium double emissions at 589.29 nm wavelengths. So here's the graph here. It says lanthanum, dense flint, barium crown, boscalate crown, and fluorite crown. Again, these are all keywords as well. Fluorite, boscalate, barium, they all came up before. Lanthanum's come up before in the crystals, okay? Wavelength, or whatever it was I was looking at. I'm losing losing my voice here. The variation of refractive index with wavelength for various glasses. My thoughts. Keyword thought here is the obsidian glass mirrors for the space elevator. We'll take these refractive light calculations into consideration when figuring out where you want the neutrino substance beam to hit the mirrors and reflect off one another, causing the spaceship momentum as it crawls upwards towards outer space from the Earth's platform, which is a type of magnet that, when turned on, will repel the bottom of your ship up from the ground using Newton's law of atoms. That's from Errol. July 30th, 2012, Google. Magnetic force repels alloys in next video. Keyword is flint. They used obsidian for flint weapons and tools, the main artifacts found in Mexico from over 300 million years ago or 3,000 years ago. Fluorite crown are keywords. A fluorite type of powder is mentioned in the listings of alloys or superalloys for the UFO designed spaceship exterior line 22f1fa19c3j to Z, if they go that high. Basically, I didn't know how high they were going to go, so I just did A to Z there for you, okay? So formula idea from the graph is fluorite plus barium plus obsidian flint plus lanthanum. Search notes data for lanthanum. Google to see what it is. I Google lanthanum in the next videos, okay? Here's the relationship between glass density and refractive index, silicate, and borosilicate glasses. There's a graph with all the different calculations in it. That shows the refractive index and the density. Okay? Relation between the refractive index and the density of silicate and borosilicate glasses. So I'm going to Google borosilicate glasses in another video and do more research on it, okay? So I'll go into the next video now.